Section 10.4, the pendulum. So we have two basic types of pendulums. What we'll most often refer to when we say pendulum is a simple pendulum. That consists of a particle attached to a frictionless pivot by a cable of negligible mass. So here's a couple examples where there's this massive bob that is on the end of the pendulum. That's the mass, has some mass m. And then there's a cable that still has some mass, but it's tiny compared to how massive the bob is that's swinging back and forth. And so if you pull it back, as demonstrated in this GIF, right, it will swing back and forth. How fast will it swing back and forth? What period or frequency will it have? Well, it turns out that assuming the angles are reasonably small, that the angular frequency is given by the square root of g divided by L, where g is our gravitational constant, 9.8 meters per second squared. Great, that's standard. L is just the length of the cable. And that's it. Notice, once again, the frequency does not depend on the amplitude, besides the assumption that was made to derive this, that these are relatively small angles. Beyond that, it just depends on the length of the pendulum and the fact that we're on Earth. It doesn't say anything about how massive the bob is that's swinging on the bottom, nor that amplitude. This is really minimal. It's a great equation. Now, a physical pendulum is when you have a cable that's not negligible mass. So a common example could be like a meter stick or a ruler, and you can get this swinging, and this is a pendulum of its own right. But in this case, I wouldn't say that all of the mass is at the full length at the bottom of it, right? The mass is throughout, and so it's a more complicated distribution of mass. So in a similar way, the angular frequency of the physical pendulum is also going to be more complicated. So we calculate with the square root of m, the mass of the object, times g, times the length of the object, divided by I, the moment of inertia. So now we're paying attention to, this is a rigid object rotating, not just a particle rotating at some distance, but the whole object itself is rotating, so our moment of inertia does come into play. What you'd end up seeing is that the moment of inertia depends on mass, and so the mass ends up canceling out, and you end up with something that looks fairly similar to g over L, because one of the lengths in the numerator will cancel out with the distance squared in the denominator, but you'll have a different coefficient, a different factor in front, like 1/2 or 1/3, depending on the shape of the object itself. So there you go. Two different ways to calculate the frequency of a pendulum. Let's look at an example of this. Example 10, keeping time. Determine the length of a simple pendulum that will swing back and forth in simple harmonic motion with a period of 1.00 seconds. When do you think we might want a pendulum that has a period of exactly 1 second? That's our grandfather clock, right? The grandfather clock has the thing on the bottom that swings back and forth. That's a pendulum, and it helps the clock keep time. Super cool. So the only thing that we are given here is that the period is 1 second, and we want to find the length in order to achieve this period. Let's take a look. We're going to note it says it's a simple pendulum, so that simplifies our analysis a bit. So we can start with our equation for a simple pendulum. The angular frequency is the square root of g over L. But we also know that the angular frequency is equal to 2 pi over the period. So if we want to ultimately be solving for the length, then first I want to get rid of the square root. So I'm going to square both sides. So we get 4 pi squared over t squared is equal to g over L. And then I want to get L in the numerator. So I'm going to multiply it across and divide by the 4 pi squared, multiply the t squared across. And so that's how we can get ultimately to this equation, that the length is just given by the period squared times g divided by 4 divided by pi squared. So if we plug in the period that we want of exactly 1 second and the g and our 4 pi squared, you end up with 0.248 meters, which is about the length of a ruler, right? And this is indeed how grandfather clocks look, where they have that pendulum swinging back and forth. That's because they're a pendulum, and the length of that pendulum sets the period of the clock with great accuracy, unless you're on a ship, right, somewhere where there's g that's changing, there's other accelerations present. But if you're in a house without earthquakes happening, this is a pretty accurate way to make a clock, because the pendulum is fixed and held just by the shape of the object, the length of the object, and by g, acceleration due to gravity. And from that, you can get a very precise timing measurement.